All right, I'm going to go over some of the trickier problems from 5.02. More specifically, I'm going to go over numbers 55 and 57 from the book, as well as number 4 from the AP prep quiz that's also on page 172. Remember that what we're doing here is we're looking for, in most cases where the trickier questions are occurring, is where we're looking for a vertical or a horizontal tangent, and we have a derivative that's been found implicitly. So our derivative is in terms of x and y. And what this needs us to do is then to solve, set our derivative equal to an appropriate value and solve accordingly for either x or y, and then go back to our original equation to find the missing coordinate, as I discussed in video 5.02. So if you haven't watched that yet, you should make sure you do so. Let's go ahead and take a look at number 55 first. All right, number 55 on page 171. Here I'm dealing with the folium of Descartes. It's given by the solutions to the equation x cubed plus y cubed minus 9xy equals 0. And if you look at page 164, there's a picture of it there on the upper right. If I read through questions A, B, and C, I find that all of these questions are essentially questions about the slope of this curve at either a point that's specified, or for me to find a point where that slope is some particular value. So I'm going to need to find the derivative, dy dx, in order to be able to determine the slope at certain points. So that's going to be kind of the crux of the problem. I'm going to find the derivative, and then for each part I'm going to apply it correspondingly. So I'm going to go ahead and find the derivative. That part should not be too challenging, and then we'll talk about the other pieces. Okay, so it's finding the derivative. I'm going to differentiate implicitly on both sides. I will take the derivative, and then going through and differentiating with y as a function of x. So derivative of y cubed is going to be 3y squared times the derivative of the inside function, so y prime, minus 9 times the derivative of xy. I'm using the product rule here, so x times the derivative of y plus y times the derivative of x, which is 1, and that equals 0. Now I'm collecting y prime on the left side and getting everything else to the right side, so I'm going to subtract a 3x squared. I'm also going to add a 9y, and then I'm going to be left with y prime, and I'm going to factor it out, and I have 3y squared minus 9x. I'm also going to factor a 3 out from each of these so that when I divide, those 3's will cancel, and I'm left with 3y minus x squared over y squared minus 3x, and that is my derivative. And so now I can go ahead and answer parts A, B, and C pretty easily. Let's go ahead and start with part A. Part A is just asking to find the slope of the folium at 2 points. So the slope of the folium is going to be given by the derivative. So at the point 4, 2, 0.42, the slope is whatever the derivative, the value of the derivative is, evaluated at that point. So all I have to do is substitute 4 and 2 into my derivative. So evaluating my derivative at the point 4, 2, I end up with 5/4. I'm going to get a negative 10 over a negative 8, which simplifies to positive 5/4. And then similarly, at the point 2, 4, do the exact same thing, and we get a slope of 4/5, which is interesting, noting that when I am flipping the x and y values here, I'm getting the reciprocal slope, which is an interesting relationship. And if you go take a look at the folium on page 164, that should make a little bit of sense. All right, for part B here, we want to determine at which point, other than the origin, the folium has a horizontal tangent. And so here's where it's very helpful to have a plan before you dive in. So I am trying to determine where the tangent is horizontal, meaning where the slope of the function is 0. And so I'm going to look at the derivative, and I'm going to set it equal to 0. Now, just thinking about how that's going to work out, I have a rational expression, so I'm going to set the numerator equal to 0. And I have a y and an x both involved in this expression. So I'm not going to be able to find both values straight away. What I'll be able to do, though, with that equation is solve for one of them in terms of the other. And then when I know, for example, y in terms of x, I can then go back to my original equation and substitute in that particular expression for y. And that will allow me then to solve for x using my particular equation, and then come back and use that x value to find y. So having a concrete plan before I dive in is pretty helpful. And if you at least think about the first portion where I'm setting the derivative equal to 0 and I'm going to have to solve for one of these variables, as we discussed in the video, then you should be in good shape. So let's go ahead and do that. So the first step is setting my derivative equal to 0, and that will happen when the numerator equals 0. And the numerator is going to equal 0. That means 3y minus x squared must equal 0. So notice that I have two variables here, so I need to solve for one so that I can use that one with my original function to determine the other coordinate point. So I can solve for y pretty easily by adding x squared and dividing by 3, and so x squared over 3. So what this tells me is that my derivative will be 0 when y is equal to x squared over 3. So what this means is that if y equals x squared over 3, I'm always going to have a horizontal tangent. But how do I figure out where this point occurs? When is y equal to x squared over 3? Well, what I can do is I can go back to my original equation, which gives me the solutions for all the points on the curve, and I can substitute in x squared over 3 for all of my y values and find what x value will make that happen. And then I can come back, and given that x value, I can find the corresponding y value. So I'm going to go ahead and substitute in x squared over 3 here and here so I can solve for x, find the x value that makes this occur. Alright, so when y is equal to x squared over 3, I can use my original equation to find the corresponding x value by setting y equal to x squared over 3. So I'll end up with x cubed plus x squared over 3 cubed minus 9x times x squared over 3 equals 0. And now I'm going to sort of notice a couple of things. I'm going to end up with an x cubed here, and I have an x to the 6th here. I have negative 9 over 3. Let's simplify that a little bit. It's going to be 3. And I'm going to get an x cubed here as well. Alright, so having done this, I can collect a couple of like terms. X cubed minus 3x cubed. That's just going to give me negative 2x cubed. Pretend that's not there. And this is going to be a negative 2. And now I can factor, because I'm setting it equal to 0, I want to write it in factored form so I can find the zeros much more easily. So if I factor out an x cubed, that's going to be pretty helpful. I have an x cubed is going to be equal to x cubed over 27 minus 2. And so now, remember, the question said other than the origin. Well, this factor tells me that x will be equal to 0, which of course will give me a y value that's equal to 0, because 0 over 3 will be 0. So I don't care about what this factor gives me. What I care about is what x cubed over 27 minus 2, what root of this equation that will give me. So x cubed over 27 minus 2 equals 0. So I can add 2 to both sides, multiply by 27, and then take the cube root. So I'm going to get when x equals 2 times 27 is 54, and taking the cube root, or raising to the 1/3 power. Okay? So when x is equal to 54 to the 1/3. And if I find what this is approximately equal to, that is going to be 3.78. Alright, so that's the x-coordinate. Now the y-coordinate, how will I find that? Well, the y-coordinate is going to be equal to x squared over 3. So I'm going to take 54 to the 1/3 and square it. So that'll end up being 54 to the 2/3 over 3. And when I calculate that and approximate it, I'm going to get approximately 4.76. So let me go ahead and write this over here. So x equals 3.78, then y is equal to 3.78 squared over 3, which is approximately 4.76. And so the point at which I have a horizontal tangent is going to be 3.78, comma 4.76. Has a horizontal tangent. Okay? All right, I'm going to quickly go over part C here, and I'm going to do that on a different page. All right, so for part C, I want to find the coordinates of a point A, which is shown on page 164, where the folium has a vertical tangent. So looking at this point, I can see that both of the coordinates are going to be positive. The x and the y coordinate are going to be positive. So that's a good thing to keep in mind. And I know there's a vertical tangent here. So this is when the derivative is undefined. So y prime is undefined when y squared minus 3x equals 0. Or in other words, I can solve again. I can solve here for x is probably the easiest one to solve for. That's going to be when x is equal to, here I'm going to subtract y squared from both sides and then divide by a negative 3. So I'm going to end up with a y squared over 3. All right, so I know the x coordinate will be given by y squared over 3. How can I find these actual coordinates? Well, I can plug in this x coordinate, y squared over 3, into my original function to find what that y coordinate is going to be. And so I'm going to go ahead and do that now. So looking at my equation, I can see a couple of things. This is eerily similar to what I got the first time around, as it should be. And what I notice here is that I'm going to have an x to this, a y to the 6th, and then I'm going to have a y to the 3rd. I'm going to have another y to the 3rd here, and again, 9 divided by 3 is 3. I'm going to do a little more simplification here. This is going to give me negative 3y cubed, and I have plus y cubed, so that's going to be negative 2y cubed. So I'm going to end up with y to the 6th over 27 minus 2y cubed equals 0. Now, let's go ahead and look again at that point A there. That point A clearly does not have a y value of 0. So we know if we factor out a y cubed, we're going to get one of the things that makes this equation true is when y equals 0. But that's not the point we're looking for. We're looking for the other coordinate. And so you'll notice when you factor out a y cubed, you're left with y cubed over 27 minus 2. And we've actually already solved this. If you go back to part B, we saw this exact same equation. We set this exact same term equal to 0, but we were solving for the x coordinate. So here we're going to get that the y coordinate is going to be equal to 54 to the 1/3, which is approximately 3.78. Now notice that that was the x coordinate we got before, and if you go back and you look at part A, you'll notice that the slopes were reciprocals of one another when you flipped the x and the y coordinates. Now, we just found in part B that the slope is 0 at 3.78, 4.76. And that means that if you flip the x and the y coordinate, you should get the reciprocal slope. Well, the reciprocal of 0 is 1 over 0, which is undefined. And so you would expect that undefined slope to occur at 4.76 as your x coordinate and 3.78 as your y coordinate, which we found here. That's the y coordinate, and that means that x is going to be equal to, going back here, x is going to be equal to 3.78 squared over 3. And when I calculate that, as I've done previously, I get 4.76. So the point that the tangent is vertical is exactly the opposite of the point where the slope was 0. So I'm going to have the point 4.76, comma 3.78 is the point A. That's the point that is labeled on page 164. All right, let's take a look at numbers 57 and also number 4 from the AP quiz. All right, number 57 asks a sort of complicated question, but it's really a simple question asked in a complicated way. So we're given this curve here, which is defined by the solutions to this equation. We want to find the normals to the curve that are parallel to this equation here. So a lot to sort of digest and break down before we dive in. Normal to a curve, that's a line that is perpendicular to the tangent. So the tangent at a point has the same slope as the curve, and the normal will have the opposite reciprocal slope of the curve at that point. And we want this normal to be parallel to this equation 2x plus y equals 0. Now here's what you need to notice. This is a straight line. Y equals negative 2x, which is just a line with slope negative 2. So if you want a line to be parallel to this line here, we need it to have a slope of negative 2. In other words, we need the normals to have a slope of negative 2. So that is kind of our task that we found. We need to find normals that have a slope of negative 2. Well, what does that mean? That means that the tangent, or we want tangents that have a slope of 1/2. Because if you have a tangent that has a slope of 1/2, the opposite reciprocal is negative 2. So if you find where the tangents have a slope of 1/2, the normals at that point will have a slope of negative 2, and that's going to be parallel to this line here. So ultimately, we're looking for the tangents that have a slope of 1/2, and so now that I know that's what I'm looking for, I'm going to find the derivative of y with respect to x. I'm going to set it equal to 1/2. I'm going to find those points, and I know at those points the normals have a slope of negative 2, and so I can write my equation for the normals to the curve at those points. So first things first, I've got to find the derivative of y with respect to x. I'm going to go ahead and differentiate implicitly and find the derivative. So taking the derivative with respect to x of both sides of my equation, and then solving for y prime, or the derivative of y with respect to x, we get that it is equal to negative y minus 2 over x minus 1. And so now I can continue on with my search for tangents with a slope of 1/2, which means that I'm looking for where the derivative is equal to 1/2. So I'll go ahead and set that up. All right, so setting the derivative equal to 1/2, and then multiplying, what I did was I set this equal to 1/2 and multiplied by x minus 1 on both sides. Now, at this point, what I want to do is I want to realize that I have an equation with x and y. So I'm not going to be able to solve for one definitively. What I'm going to need to do is need to actually solve for one in terms of the other, and then use that value. So for example, if I solve for y, I can use whatever I get from y in my original equation. So I can set that y value to whatever that expression is equal to in my original equation in order to solve for x. So I'm going to go ahead and solve for y here. And in doing so, I get this expression here, that y will be equal to negative x over 2 minus 3/2. So to take stock of where I'm at right now, I know that my derivative will be equal to 1/2 when y is equal to negative x over 2 minus 3 over 2. So I want to find where this point exists. So in order to do that, I'm going to set my y value equal to negative x over 2 minus 3 over 2, and then find the corresponding x value that will make that occur. So going back to my original equation and substituting this in for y will allow me to do that. So setting y equal to negative x over 2 minus 3 halves gives me this expression here, and I'm now going to solve for x. So setting y equal to this expression and then solving for x here to get the x value at which when y is equal to this. And when I go through it, I get to this point here, I notice I have a lot of halves. So if I multiply both sides of my equation by 2, that'll help clear those out. And I'm still going to end up with 0 on the right side. So now on the left side, it'll be a lot easier to work with, and it'll allow me to factor a little bit easier. So after doing that and collecting like terms and then factoring out a negative, because I don't really like to have a negative x squared there, it just makes it a little easier. And I've set it equal to 0, so I'm going to try and factor in order to solve. And so in doing so, I can factor this pretty easily. Negative 3 and 1 will multiply together to be negative 3, and they will also add to be negative 2. Alright, and so that gives me two options. So x equals 3 or x is equal to negative 1. And these are the x values for which my derivative is going to be equal to 1/2. Now, when I know the x values, I'd like to know the corresponding y values. So I can go ahead and plug the x values that I found back into my equation that relates x and y when the derivative is equal to 1/2. So when x is equal to 3, I'll have negative 3 halves minus another 3 halves. That'll be negative 6 halves, which is negative 3. So 1 point, I'll write them here, is going to be 3, negative 3. And when x is equal to negative 1, I'll have negative times negative, which is positive, so I'll have positive 1/2 minus 3 halves, and that is going to end up being a negative 1. So I'll have the point negative 1, comma negative 1. So these are going to be the 2 points at which my tangent have a slope. My tangents have a slope of 1/2, which means that the normals will have a slope of negative 2. So now that I know the points at which the normals will have a slope of negative 2, I can now write the equation for each normal line that passes through these points. So the first one will be y plus 3 is equal to, now the slope, this is where the tangents have a slope of 1/2, so the normals have a slope of negative 2 times x minus 3. You can simplify that into slope-intercept form if you'd like. So that'll be one equation, and the second equation will be y plus 1 equals negative 2 times x plus 1. And those will be the two equations for the normals where the normals have a slope of negative 2. All right, so here's the AP quiz number 4. It's a free response question. It says there's a curve defined by this equation here, and you want to find dy dx. That's part A. Part B, you want to find an equation for the tangent line at each point on the curve when x is equal to 1. And part C, you want to find the x-coordinate of each point on the curve where the tangent line is vertical. So part A is very simple. I'm going to differentiate on both sides and solve for the derivative of y with respect to x, or y prime. Part B, I'm going to find an equation for the tangent line at each point on the curve with an x-coordinate of 1. So when x is equal to 1, I'll need to evaluate the derivative at that point to find the slope, and then also find the corresponding y value. I might need to find the corresponding y value first, though, depending on what my derivative is. And then I can write the equation for the tangent line at those points. And then for part C, I want to find the x-coordinate of each point on the curve where the tangent line is vertical. So I'll need to take my derivative, and I'll need to find out what will make the derivative undefined. So set my denominator equal to 0 and solve. So let's go ahead and get started with part A. Alright, so taking the derivative of both sides, making sure to use all the rules of implicit differentiation in accordance with also the product rule here. And now I'm going to isolate my derivative, and that way I'll have an equation for the derivative dy dx. So there I've found my derivative. It is a rational expression, so that's definitely going to help for part C, where I'm going to be looking for a vertical tangent. At part B, I want to find the equation for the tangent line at each point on the curve with an x-coordinate of 1. So the first thing that I've got to do is I've got to actually find all the points with an x-coordinate of 1. Well, how am I going to do that? I know x is equal to 1, so now I need to solve for y. So for part B, when x equals 1, what do we have? Well, we're going to have the equation y squared minus y equals 6. And what I'm going to do is I'm actually going to subtract 6, so it'll be minus 6 equals 0. And so now I can go ahead and, since I have a quadratic set equal to 0, I'm going to try and factor so that I can more easily find the y values that make this equation true. So after factoring, factors to y minus 3 times y plus 2. I'm going to get two y values, y equals 3 and y equals negative 2. So I have 2 points that I'm considering now. So I have the point 1 comma 3, and I have the point 1 comma negative 2. And at each of these points, I want to find the equation for the tangent line. So the equation for the tangent line is going to need a slope at each of these points. So what I'd like to do is evaluate the derivative at each of these points. So what I'll do is I'll have dy dx evaluated at this point 1 comma 3. And then I'll also have this derivative evaluated at the point 1 comma negative 2. So after evaluating, here I get that the derivative at 1 comma 3 at this point is 0. So that allows me to write the tangent at that point as y minus 3 equals 0, because it'll be 0 times x minus 1, which is 0. And so that's the line y equals 3. Of course, it's a horizontal line with slope 0. And the derivative evaluated at the point 1, negative 2 has a value of 2, so I can write the tangent at that point as y plus 2 is equal to 2 times x minus 1, and so I get the equation y equals 2x minus 4. So these are going to be the two equations for the tangent to this curve when x is equal to 1. Now part C wants me to find the x-coordinate of each point on the curve where the tangent line is vertical. So I'm searching for the x values where the tangent line is vertical, meaning that my derivative must be undefined at those points. So I'm going to try and find when y prime will be undefined. I'm going to go to a new page to make that happen. Alright, so for part C, my derivative is undefined when the denominator is equal to 0. So when x times 2y minus x squared is equal to 0. So now the solutions to this particular equation, one solution is that x equals 0. That's the first one, by setting this factor equal to 0. Now, this would be great. This would be a wonderful answer if x equals 0 was a coordinate of my original equation. In other words, if x equals 0 was a possible value of x. But I've got to check that. So what I need to do is I need to take a look at my original equation, which was x times y squared minus x cubed y equals 6. Now, I can see that if x is 0, I'll have 0 minus 0 equals 6, which means that x equals 0 does not work for this particular equation. So this is not an x coordinate that allows my derivative to be 0. Okay? In fact, this is not a point on the line. So this is not going to work out for me. It's a bummer. My second option is that 2y minus x squared equals 0. Now, here I have two variables, and since I'm hoping to solve for x eventually, let's solve for y here. We'll get an expression in terms of x, and we can plug that back into our original equation to solve then for x. So solving for y, I'll end up with y equals x squared over 2. And when y is equal to x squared over 2, I'll be able to substitute that into my original equation and solve for x. Alright, so substituting in x squared over 2 for y into my original equation, here I'm going to have an x squared squared, which is going to give me x to the 4th over 4, because 2 squared is 4, and then times x, so it'll be x to the 5th over 4. Minus, and now here I'm going to have x cubed times x squared, which is going to give me x to the 5th over 2, which equals 6. Alright, well, notice something here. I have x to the 5th over 4 minus x to the 5th over 2. These are common terms, right? If I have a fourth of something minus a half of something, well, then I have negative a fourth of it, right? If you have 25 cents and you owe someone 50 cents, all of a sudden you're in debt 25 cents. So this is going to be negative x to the 5th over 4 equals 6. Now, solving for x, I'm going to multiply by negative 4 on both sides, which is going to give me x to the 5th equals negative 24. Raising each side to the 1/5 power, I then am able to solve for x. X will be equal to negative 24 to the 1/5, or the 5th root of negative 24. So before typing this into your calculator, there's a little bit of observation that you can make. The first is that you have a negative number raised to the 1/5 power. You're trying to find the 5th root of some negative number, which means you're looking for something that you can multiply by itself 5 times to get negative 24. So clearly it's going to have to be negative, because a negative times itself an odd number of times will still be negative. And you're multiplying it by itself 5 times to get 24 as an absolute value. That's not going to be a very big number, right? I mean, if you take 2 to the 5th power, you're already bigger than 24. So with that in mind, you can go to your calculator and compute. And hopefully you got something in between negative 1 and negative 2. So this is the only x-coordinate. Remember, the x-coordinate that we found originally, x equals 0, that first one does not work. And so the only one that does work is when x is equal to the 5th root of negative 24.